All right, I think we're recording. Who knows? Who knows? We got the spinning beach ball. Okay. There we go. So let's say we are recording, okay? We're on example 1B on section chain rule 2.6, okay? So first of all, we use the chain rule when we're taking the derivatives of what type of functions? Composite functions, right? Functions inside of a function. And sometimes rewriting it so we can see the layers is helpful. Sometimes adding grouping symbols where there are none can help us see the layers, right? Help us see the layers. So this is the derivative with respect to x of not just sine of x, but sine of 5x. And so 5x you could think of as being the inside function. It's inside the sine function. So I would probably add parentheses there. And now I would call that sine a blob. So how many layers do we have? 2, right? Sine on the outside, 5x on the inside. So how many factors should we have in our answer? 2. Okay, good. So working from the inside out or the outside in? Outside in, right? Okay. Unless you happen to be on the inside, then the only way to get out is just to fight your way from the inside out, right? Maybe, yeah. You're going to see it doesn't really matter if you work from the inside out or the outside in, because you're going to get the same answer. But I prefer to start on the outside because that's where I'm at. What's the derivative of sine of blob? Cosine blob. Good. Now, when you take the derivative, of course, the d dx goes away, and you get the same blob. You don't take the derivative of the blob right away, do you? No. Times, and then by the chain rule, the derivative of the inside function, what's the derivative of 5x? 5. Cool. Now, because multiplication is commutative, you could just call that 5 cosine of 5x, right? And as you do the chain rule enough times, you might not actually unpack the boxes or those Russian nesting dolls to the right. You might start unpacking them to the left, which would be fine. It would just save a little bit of writing, or rewriting, I should say, at the end, right? But sometimes if it comes like in the middle of a problem, you already have a term in front of there, unless you anticipate, having other Russian nesting dolls unnested in front of it, then you might not have enough space. Okay, let's go to C. I got the derivative with respect to x of blob, right, to the 7th power. So there's 2 ways to do this, right? We said you could expand it out. No, thank you. Or we can use the chain rule. So here we go. Blob to the 7th power by the power rule would be 7 blob to the 6th. And notice I leave parentheses there for the blob. Is it okay then now to say, okay, the derivative of the blob, 3x minus 2, is 3? No, 1 at a time, right? So you just rewrite the blob. It's in there. And now times the derivative of the blob, which is 3. And of course, you can then combine your like factors. 7 times 3 is 21. 3x minus 2 to the 6th. And you have a working derivative before the person who doesn't know the chain rule is still trying to expand that just to get to the point where he could be OTC. You're done. So far, so good? Nothing so good so far. Nothing to it. There's nothing to the right. Let's try going to the left. All right, A, B, C, D. Here comes D. On your mark, it said you try. Remember, if you have multiple terms, it's just like 2 little problems in one. You just treat each term separately, right? Each term separately. And once you take the derivative, do you put the d dx? It goes away. Yeah. Great question. Great question. This is why I let you figure it out on your own. Here's the thing. What is being squared in that second term? Is it the tangent of x, or is it just the x, or is it just this top right tip of the x? Or is that 2 even supposed to be there? It's just the x. Very good. If you ever see a single term following a trig function or an inverse trig function, and there are no parentheses, then you just take that entire term to be the angle. Okay? So adding grouping symbols here like this is what I would do, because it's tangent of the angle x squared. You wouldn't need them. That's tangent times x squared. There you go. Tangent of x squared. So the first term then becomes 1. That's pretty easy. And now you walk up to the second problem, and with the parentheses in place, you just see tangent of blob, right? So what would be the derivative of tangent of blob? Secant squared of the same blob. Now what about this minus sign? Is it still there? Yeah, it's minus. Now times the chain rule, the derivative of x squared. What's the derivative of x squared? 2x. Is it okay to multiply it on the left instead of the right? Yes. Now you don't have to, of course, but as you do enough of the chain rule, you're going to know that you're going to have another factor that's generated. And so as you anticipate it, even in the second term, this is what I'm talking about, you can kind of leave a little space for it and just multiply the chain rule on the left side. Nothing wrong with multiplying on the right side. You're always going to have space on the right side, yes? And then you can kind of just rewrite it on the next line. But we do want to be efficient, right, as well as effective. I guess efficiency would be the secondary goal. What would be the tertiary goal? Enjoyment. Effective, efficient, and then we want to enjoy it. Fun, 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 fun. All right. Do we need the chain rule for this one? This is kind of looking like something from 2 sections ago, right? I spy a quotient. Do you? Yeah. So what is this doing here? I don't know. Let's just work it like we know how. Let's use the what rule? Did you say Heidi-ho rule? Wow. Start with a ho, end with a ho. Ho's are on the outside. Ho-de-hi rule. Okay, so here we go. Ho. What's d-hi? 0. We are recording. Ho-de-hi minus hi. What's hi? 1. And what's d-ho? 1. All over ho, ho, or ho squared. That wasn't that bad. Now, if we clean that up a little bit, what happens to the first term in the numerator? It goes to 0, and we have minus 1 over this, x plus 1 quantity squared. There it is. There it is. My mistake. I put it in the wrong section, right? No, you would think so, right? No, there's another way to do this, and it might be faster, especially if we want to take derivatives of higher orders. We can actually bring the x plus 1 quantity to the top and call it all to the what power? Negative first. That now becomes a what rule? Chain rule, because I can't distribute the negative first exponent. I have blob to the negative first. And let's see if it works. By the chain rule, blob to the negative first becomes negative blob to the negative second times the derivative of the blob. What's the derivative of x plus 1? 1. And if you clean that up very, very quickly, you get negative 1 over x plus 1 squared. Same thing. And it's almost a little bit more efficient, remember, and that's our secondary goal. If we had to take like multiple derivatives, like higher order, if we need to take another derivative, we can still use the Ho-de-hi rule every time, but if we keep it in this format right here, it's ready to go by another chain rule. We're down here, the Ho-de-hi rule, d-ho is going to require now a chain rule inside the quotient rule. So look for opportunities to do something like this whenever you have a constant over a function. If you had like a variable in the top, then if you bring it to the top, you're going to have a product rule with the chain rule inside. But if it's a constant, it's going to work out very nicely with the chain rule. So constants over functions, look to do something like this to speed up the process. Just an option. What's nice to know is that if we do it 2 different ways, we get the same answer. How does the math know to get the same answer a different way? How does it know that? How does it all just work? How? I don't know. Google teleological argument. How does it all just work out? Okay, look at this one. The derivative with respect to x of sine squared times 3x? No, of 3x. Is that going to require the chain rule? Yeah. How many layers do you see? maybe two obvious layers. I don't know. Whenever you see something like that, like sine squared, cosine cubed, sometimes it's like the natural log, something like that. That's the condensed version. Mathematicians like to kind of abbreviate things. It's kind of like having a compressed or a zip file that's sent to you. You need to kind of uncompress it or unzip the file in order to access it. If you ever see something like that and you're doing the chain rule, especially in the beginning, it's worth it to expand it. Okay, it's the whole sine squared. And then on the inside we have sine of, and then we have a 3x, which is more than just a plain old x. So now how many layers do you see? Maybe I should put the sign in a different flavor too. Grape. There we go. I see 3 now, right? So you walk up, you get inside the brackets and you're like blob squared. There's 1. And then the next layer inside is sine of blob. That's 2. And then the blobbiest of blobs, the innermost blob, is 3x. So you have 3 layers. How many factors should you have in your answer? 3. There you go. 3. Or would it be like this? How is it? 3. Right? I don't know. Okay, we work from the inside out or the outside in? Outside in. You want to try from the inside out? No? Okay. If you're comfortable with the outside in, that's fine. So it'll be blob squared, which becomes 2 blob to the first. And remember, we just rewrite the blob. Times, the next layer is sine of blob. What's the derivative of sine of blob? Cosine of blob. It's kind of nice to switch flavors here every time we have another layer, just to help you see it. And then the innermost blob, the blobbiest of blobs, is, the derivative is 3. So there's the derivative. Now if we simplify, we get 2 times 3 is 6. Sine of 3x times cosine of 3x. Notice also that every time we take the derivative, each factor is getting more diminutive, right? Increasingly diminutive, smaller and smaller. And that makes sense because we're unpacking boxes that are within boxes, right? And the only way for the little box to fit in the big box is, of course, if it's littler. Now, 6 sine of 3x cosine of 3x. That's correct, yeah? Everyone agree? What if you do this problem and it's a multiple choice question and that's not an answer choice? Do you panic? No, you never panic. Because this right here simplifies to something else. 2 sine blob, cosine blob. 2 sine blob, cosine blob is equal to sine of 2 blob. There's a double angle identity right here that we can use. Yes, yes? Now, this x in the double angle identity could be anything. It could be x, it could be y, it could be 3x, it could be peaches, whatever. In this case, it's 3x. So if I condense it down, 2 sine blob, cosine blob is going to equal sine of twice the blob. What's twice 3x? 6x. And that takes care of all the highlighted part, but I still have, guess who? I still have the factor of 3 there. Bless you? Okay. It usually does. Right here. Yeah, so both of those are correct. You do need to know your double angle identities. Sine of 2x equals 2 sine x, cosine x. And, of course, let's review cosine of 2x while we're here. Cosine of 2 blob, that's the one that looks a lot like, not Papa John, but Papa Pid. Cosine squared minus sine squared of x. It just has a minus sign in between there. Okay. Papa Murphy, another pizza papa. All right. How are we doing? We got a few minutes left. You feel like diving into this one or saving that one for another day? Let's save it. Let's save it. It is a Friday. Okay. We'll stop right there then. That's good. Just Google teleological argument. All right. So we'll stop right there and we'll pick up with G on Monday.